Thank you very much for the warm welcome. It's hard for me to believe that I'm on this stage today talking about fault tree analysis in Kafka, because a year and a half ago, I didn't know that fault tree analysis existed. I didn't know what it was. I also was a novice at Kafka at best. So what happened in this year and a half of time? Well, the first thing that happened was I attended my first SREcon in San Jose. At that SREcon, I found Emil Stolarski's talk about how oil companies use fault tree analysis to avert disaster, an inspirational talk. I didn't really connect the dots at the time, but another thing I learned at that SREcon was how to measure what matters, things like SLOs and such. I also rekindled my previous passion for being a systems administration. About 13, 12 years ago, I was a sysadmin at a small company, small startup in New York. And when I was a sysadmin then, I remember working really hard to get out of systems administration and upskill my career to become a software developer. At that SREcon, my first SREcon, I kind of realized that SRE as a discipline could be an upgrade to that developer track that I was on. So 6 months after attending SREcon, I actually accepted a job at Lyft as the third reliability engineer. Of all things, at that job, I was tasked with setting up reliable Kafka clusters. It was a new job, and my skills, and I wanted to make a good first impression. And my skills on Kafka were still kind of novice level. So I needed to do something to quickly upskill myself in Kafka. So I just decided to try out to draw fault trees for Kafka and see where it would take me. Conveniently, by drawing these fault trees, it allowed me to see the failure points that I'd have to worry about with Kafka, and it helped me figure out ways to work around them. So lo and behold, it was a very successful experiment. I figured out that the math with fault tree analysis also helped me define service level objectives, which are central to my new role. Managers were impressed that I was able to show them some math on how much Kafka would cost and what that cost did to reliability. I conveniently had some pictures to show them as well. And fellow peers were impressed that I was able to build really reliable Kafka clusters almost on the first go-around without wasting a lot of time making mistakes. This success, I have to give credit where it's due, and this is going to be kind of cheesy, but SREcon in San Jose, it up-leveled my career, and I'm very thankful for it. And I hope that maybe there's people in this conference that maybe this is your first SREcon, and maybe the same thing will happen to you. If not from this talk, then maybe from Nancy Levinson's talk, from the opening plenary, or some of the many other talks that you heard this week. So the first thing in this talk I'm going to do is explain what Kafka is, why we care about it, especially for those of you who are not familiar with it. In this part, I'm going to define what we want to measure and what we want to tease out of Kafka in terms of reliability. The second part, we're going to take a little detour and build some tooling that we can then approach to dive into building fault trees for Kafka itself. We'll create fault trees for availability and data durability service level objectives. And then if I'm still standing, I'll have a conclusion with some references, thoughts for the future, and takeaways. So first things first, what is Kafka? Kafka, on a very high level, is a reliability tool. It is there, at least the way we're using it, it allows us to move data around the network without losing it, or at least minimizing that data loss. You can skip the Kafka business altogether and do point-to-point connections, but there's a lot of edge conditions that you're going to have to worry about to make that reliable and to be productive with it. I'll give you some example use cases in a little bit, but because data is very central to a lot of companies today, especially Lyft, Kafka gains very high stakes usage, and reliability of it is extremely important. One example is the observability use case. You might have several thousand servers, if you're successful, that are emitting metrics and logs. You usually don't know what rate these servers are going to be emitting these metrics and logs at. You want these metrics and logs to go into metrics and visualization systems like Wavefront or OpenTSDB, and your logs to go into things like Elasticsearch. Again, in the point-to-point model, you're going to significantly have a lot of complexity pushing it into something like Elasticsearch because it wants to consume at a certain rate, but your servers might be producing logs at whatever rate they want. Kafka acts as a distributed buffer to allow you to produce at the pace that your services want to produce at, and your consumers produce at their own pace. If Kafka is not reliable in this use case, then we drop the ball on users finding problems before we do. Another use case is event streaming. This is very near and dear to Lyft's business. We have mobile apps that are used by drivers and passengers. And these mobile devices, they beam events, maybe location events, or if a passenger or driver is tapping on the app, events get generated. They flow into our kind of distributed buffer. And then we fan out all of these events into various microservices, data stores, et cetera, so that we can provide functionality back to the users or to the business. If Kafka is down in this case, then we're either going to provide a degraded user experience, or we're going to provide no user experience, in which case we'll lose revenue. A third use case is change data capture. Lyft has a lot of microservices, and a lot of these microservices use their own separate databases. These databases will generate a transaction log as transactions get, or data gets added to them. They'll get pumped into Kafka, and then we'll aggregate all of these database transactions together and collate them into a central database where we can do business reporting and things like that. For this use case, data durability is extremely important, because if you lose any data after you've written it to Kafka, then you might misreport something which might have legal or financial implications. So again, Kafka's very high stakes in all three of these use cases. So we've identified why Kafka is important and roughly what we use it for. Why do we want to go through an exercise of trying to quantify its reliability? Well, the first thing we want to do is we want to create a forecast on how Kafka might misperform and for how long. If we know that Kafka will be down for a long time, then we might need to create a redundant set of Kafkas and pay that appropriate cost. On the other hand, if we can predict that Kafka will be down for short periods of time, then maybe we can solve that problem by just adding a little bit of memory to producers so that they can retry once Kafka comes back up. Again, we can balance costs if we know in good detail what our reliability thresholds are. Our reliability thresholds, we define the following service level objectives for Kafka. Again, maybe they're more upskilled Kafka experts here than us, and we might be missing something. Let us know. The first is availability, whether we can write or read to Kafka. Second, data durability, whether after we've written to Kafka that data goes away. And latency, how fast does data go from point A to point B? For availability, what's important is we need to predict how long Kafka might go down for and how often it might go down. Again, in that, if you can guarantee that Kafka will go down for 4 minutes, then you can figure out how much memory your producers would need and pay that cost for that memory so that they can withstand Kafka going down for those 4 minutes. If you can bring downtimes down to 2 minutes, you then pay for less memory on your producers. That's just one example why this service level objective matters. Durability, you care about how much data you lose and how often you might lose it. And then latency is interesting because the higher latency is, the higher the chance that something will go wrong. So you want to keep latency low to keep your other reliability guarantees high. So let's now dive into fault tree analysis and go over some basics. Fault tree analysis was invented by Boeing in 1962. It was invented when Boeing was working on launch control systems for the Minuteman ICBM systems. Talking about high-stakes usage, this was it. I mean, you might, if you're dealing with nuclear weapons launching, you might, if one failure could be that you friendly fire yourself. Or in an even worse case, if you don't launch the missiles at all, then you'll lose a war. Boeing wanted to accomplish two things with fault tree analysis. First, they wanted a structured way to list out all of the possible failure points in the system that could contribute to a launch failure of different types. The second thing they wanted to do is they wanted to have a way to prioritize which of these failures they needed to work on, hone in on, and engineer around. The technique was very successful for them, and it has since gotten adoption in the aerospace, military, petrochemical, pharmaceutical, oil and gas, and many other industries. The starting point for fault tree analysis is a little bit of definitions. The first part is event symbols. There are basic events. These are the starting points of your a starting point for your failures. For example, an earthquake is an example of a basic event. An intermediate event is an event that either ties in one basic events, multiple basic events, or other intermediate events. So for example, server falling out of rack would be an intermediate event, and you could say that earthquake is a basic event that feeds into server falling out of rack. And the third event symbol is a transfer event. You would use this kind of like a computer method or function where you group multiple sets of intermediate and basic events or subtrees and copy and paste them around in your diagram when you have repeating things. There are gate symbols that tie these events together. In this talk, we're only going to cover two of them. OR gates and AND gates. There are NOR gates and XOR gates and other symbols, as you'd expect with this type of stuff. An OR gate says that any events under the OR gate, if one of these events fails, then it'll cause the intermediate event above it to happen. And AND gates do the opposite, where every single event under the AND gate has to occur for the failure above it to happen. So let's dive into an example. Let's take a RAID 0 array. A RAID 0 array is striping RAID. There's no redundancy here. If you lose any of the disks in your RAID 0 array, you will fail to write to this array, or read for that matter. So we'll use an OR gate here. The first thing you need to do is you need to assign a failure probability to your disks. I'm going to choose 4%. Yaniv's talk said it was 1.5%. That's true under certain conditions. When you're setting these probabilities, you want to set a reasonable upper bound. There's a 2007 paper by Google where they studied a large set of disks and their failure rates. They actually fail with a bathtub curve, where in the beginning of the life cycle, there's 5 to 6% failure rate. Then after about half a year, you see failure rates closer to 1%. And then they go back up after several years to 5 to 6%. So I'm taking kind of a little above or a little below the rim of that bathtub and saying 4%. And it's a conservative estimate. These failure scenarios happen over a period of time. In this case, we're going to use AFR, annualized failure rate. Then you do some math. This is standard probability theory for independent events happening in an OR scenario. You add the probabilities together, and you can optionally subtract the probabilities, or product of the probabilities. Note that the percentages are small, or your failure rates are small in our example, so what you're subtracting is going to be inconsequential, so fault-free analysis gives you the liberty to do a little less math. So what we get for a RAID 0 array is 12% chance of failure. So now let's look at a RAID 1 array. For a RAID 1 array, this is mirrored RAID. You need all 3 disks to fail for your writes and reads to start failing. You use the AND gate there, so you use standard probability theory to get your failure rate. And what you get is a very low failure rate. And because a lot of us are reliability engineers, we kind of switch to nines notation here so that we don't look at multiple decimal points after multiple zeros after a decimal point. So there is one caveat with what we just did with RAID 1. That is the chance of success if we don't remediate. It's very likely that if you're running a RAID 1 array, that you're going to replace your disks when they fail. So we need to factor that in to calculation. So what we need to do is we need to figure out how quickly are we going to remediate these RAID 1 disks. So I'm going to pick 3 days. I have a server at home that I love almost as much as my wife. And what happens when a disk fails is, well, I need a day to go and buy a disk, maybe overnight it from Amazon or something. And then I have to replace it. And then it takes another day to maybe copy the data over. When I'm out of town, I call my wife and she replaces the disks. And if both of us are out of town, we scramble all the neighbors that we can find, post on Nextdoor, It's a whole process. So as you notice, by having a remediation rate of 3 days, our success probability increases tremendously. So we can make a decision and chop off one disk and go down to a RAID 1 array with 2 disks. Your chance of success goes down, but it's still fairly high, especially for home use. So the formula for computing failure probabilities with a remediation rate is as follows. For those of you who are allergic to math, I'm not going to read the middle formula out loud. If your failure probabilities are low, under 10%, you can take a shortcut in fault tree analysis where you multiply the probabilities together and then multiply them by your remediation rate factor, which is T in this case. T in the previous example was 3 divided by 365 in case any of you want to redo the math. So now we have some basics under our belt. Let's get into the meat of this talk, which is drawing fault trees for Kafka. So we're going to first start with availability. We want to find out what our probability of writes and reads failing are. And in the back of our minds, we're going to try to target a 4.9 success rate per year. That's going to be about 43 minutes of downtime in a given year, which averages out to, I believe, like 4.3 minutes per month. So we'll start really simple. We'll start with a Zookeeper and a Kafka broker, just one of them, both single points of failure. We first need to think about what's going to cause our Kafka broker to fail. Well, we're going to use rotational disks because it's cheap. And we know that they fail at 4%, as we discussed earlier. Another thing that we notice fails is the network. We get network partitions. We assign a 2% chance of failure for that. Then you can have just general hardware failure. We're going to assign 1% for that. And you can get kernel panics, other type of OS faults. We're going to also assign 1% for that. There's probably other things you can think of, like operator mistakes. You can feed that in here, like whatever kind of you see in your environment, you would want to feed in to this diagram. So then we have to determine the failure rate of Zookeeper. So Zookeeper, let's assume it's running on its own host. We'll use solid-state drives for it, because that's the general recommendation if you're running Zookeeper, to run it on SSDs. SSDs fail with 0.8% chance. Zookeeper is going to have the same network partition, OS faults, and hardware problems. So then we find that Zookeeper is going to have a 4.8% chance of failure. Kafka, 8% chance. And you're going to get a total of 12.8% chance of failure in a given year. So let's try to improve the system. Kafka has replication features. We can run 2 brokers and enable replication across them. So we're going to use our first transfer event. We're going to use it to denote a Zookeeper. Both Kafkas depend on a Zookeeper. So instead of drawing it out and making the diagram super wide, we use the transfer event. We're going to refactor the diagram a little bit more. We have that transfer event for Zookeeper. We create a separate transfer event for host failure that's not related to disks, which is common between Zookeeper and Kafka. And then we have a transfer event for Kafka itself. So now your broker is going to have 2 transfer events, Zookeeper and broker itself. So we'll plop in our failure probabilities. And with 2 brokers, we get 98.4% chance of success. So that's a little better. So we have one single point of failure at this point, which is Zookeeper. So let's create 3 Zookeepers instead of 1. You generally add Zookeepers in odd sets. So that's why we jumped to 3 right away instead of going to 2. What you now get is almost 2.5 nines of availability. That's a lot better. Let's keep going and add a 3rd broker. When you do the math, you get 3.5 nines of availability. So we're much closer to 4 nines here. So let's look at a few other scenarios. If you look at the middle scenario, 2 brokers and 5 Zookeepers, you'll notice that the success probability doesn't increase. You add 5 Zookeepers, you're burning cost without adding additional reliability guarantees, because Zookeeper doesn't dominate your system's reliability. The number of Kafka brokers does. You just need a base set. As long as Zookeeper is not a single point of failure with 3, that's good enough, at least according to the math that we've done. The other thing to keep in mind is when you're dealing with Kafka, you have to keep the in-sync replica setting count. If you set it to 1, as was the assumption in the fault tree, then you're allowing, you only push back on writes when you're down to 1 broker. With ISR equals 2, you start pushing back on writes after you lose a 2nd broker. So if you have 2 replicas with ISR 2, you're still good. Once you lose that 2nd replica, you're not good. So you have to treat it as 2 brokers instead of 3 brokers when you're doing 3 brokers with ISR 2 and replication factor 3. One way to get to 4 nines of availability is to go to replication 4, so add a 4th broker, and keep ISR equals 1. The general guidance that I would highly recommend is to keep your ISR at 2 for data durability. So you probably would do 4 brokers and ISR 2 to get that 3.5 nines. We're still not at 4 nines with that scenario. Note that I have this cost per 9 column, by the way, that I forgot to talk about. It's kind of a fudgy number, but it gives you a sense of how much, whether you're spending money for no impact on your reliability. One way to get 4 nines is to switch to solid-state disks. Kafka will take them just fine. It's a little costlier, but you get that extra 9 of availability. EBS is another way to get to 4 nines. EBS disks at AWS advertise that they fail at 0.2% chance of failure. The only problem is you spend a lot of money if you want EBS disks that give you similar tail latencies to rotational or solid-state disks that are non-shared. So we've covered availability. Let's dive into data durability. Let's see if we can get 7 nines of data durability, which I believe is losing 100 messages for every billion messages that you send. The first thing you need to think about for data durability is how long does your remediation rate occur? Because you're not just going to leave your broken Kafka hosts down after they go down. You're going to hopefully go and remediate them in some shape or form or another. The first question you need to ask is, OK, how much data am I going to have worst case on a broker? Let's, for example, assume 6 terabytes, which happens to be the amount of data that you have on a D2X large instance on AWS. The next thing you have to think about is, what is the replication rate? On those D2s, empirically, you get about 70 megabytes per second transfer rate. between brokers. That would mean that it's going to take you 24 hours to replace a broker when it goes down. And that's assuming that there's no, you're not waiting for humans to go in and replace these. So we'll start off a little simple. We're going to just straight away use 2 brokers and assume that there's only one 6 terabyte disk. You remember the failure rate formula with remediation rates? When you do the math, you get a pretty strong durability guarantee, higher than our target right out of the gate. However, on AWS, you don't get a 6 terabyte single disk. You get 3 2 terabyte disks. On the D2 instance, you get 3 disks, 2 terabytes each. And when you lose any of these disks, AWS takes the instance away from you. So you might as well just maximize the storage space provided by these disks and use RAID 0. So when you compute the failure probability, we drop below our targets. And remember, this is 2 brokers. So for availability, we kind of want to run 3 brokers anyway. So we'll do exactly that. And we're back on track. Very strong durability guarantee with 3 brokers. So now let's, for fun, make a decision. Our Kafka clusters are very popular, and we want to have them support more data. So we're going to see what happens when we bump up to the biggest, the beefiest D2 instance that AWS provides, which have 48 terabytes per broker split across 24 2 terabyte disks. Our replication rate is going to be the same. The network didn't change. The remediation rate changes drastically because now it takes 8 days to replicate a full broker. That's assuming you're retaining your data for those full 8 days. Same assumptions apply. Again, we're going to use RAID 0 on these 24 disks because you lose the host otherwise. So you maximize the storage space. And your durability, with that decision, your durability guarantee goes down substantially. It's not safe anymore. So the moral of the story of durability is, you generally want to keep smaller units of data and scale horizontally rather than vertically. And this kind of has some math behind decisions like this. One thing that we're not going to cover in this talk is latency. Fault tree analysis is tough to mold into trying to figure out your latency SLOs that you want to sign up for. It's best to experiment with worst case loads or ramp your load up until your latencies become uncomfortable and then throttle your users at that comfort zone load. It's a tough problem. Maybe we'll have another talk about that at some other point. So for those of you in the back of the room that might have probably had trouble reading the diagrams, don't worry. You don't need to see the eye doctor after this. You can find all of the pictures and all of the slides on github.com/falko/fta-kafka. You can look at the pictures at your own preferred zoom levels. The tool that I used to generate the fault trees is also on GitHub at rakimov/scram. It's open source. I've included a few links that you'll find on the first GitHub repo that you can use to learn more about it. Everything there is what I use to learn about fault tree analysis. So the things to take away. fault tree analysis might help you put some rigor and math into determining your service level objectives. You can use it to uncover cost savings without doing much tinkering. And generally, it's a good framework to use when you want to check decisions to see if you might counterintuitively reduce reliability with a decision. Some things to look in for the future. There's kind of a drive, at least at Lyft, to get Kafka and Kubernetes so that we have a unified provisioning stack for the whole company. I kind of worry about it because I don't know how Kubernetes rolling restarts might affect Kafka. So more analysis, I think, would be prudent there. With Kafka improvement proposal 500, the Kafka community is going to be removing the Zookeeper dependency. In theory, that might increase reliability. So we might need to update the fault trees accordingly. SREcon19 is the tool that I used to generate the fault tree analysis diagrams. It's a little difficult to use. I think we're all empowered to contribute to it since it's open source. And another interesting idea that I'd offer up is distributed tracing has a lot of data that you could use to generate fault trees. And you could get empirical failure rates from your distributed tracing data and tie it all in together. And that might help you prioritize which components you should target when trying to increase reliability of your overall system. So thank you all for listening. I hope the talk is as valuable to you as the other talks at this SREcon and previous SREcons were valuable to me. Hope that maybe this or something else will up-level your careers as all of this up-leveled mine. Feel free to reach out to me at any of these places. And without further ado, thank you all very much.